So, we were doing right, we wanted to understand Stirling numbers of second kind. Is some feedback loop, guys? Okay, is it okay? Right, so we define this number n curly k as the number of ways to partition a set of size n into k disjoint subsets, non-empty disjoint. So, from the definition we had a recurrence very similar to the binomial coefficients. We had that, right, either you can put the last element all by itself into one single partition, then the remaining n minus 1 you have to partition into k minus 1, or you partition n minus 1 into k partitions and put the last one in one of these k, right. From this doing the, so we defined a generating function, we kept k fixed and n varying, right. So, we defined it this way and then we multiplied x raised to n both sides, summed it up and solved for a recurrence. We got that for the generating function, we got that sk of x is x raised to k upon this product of linear terms, right. So, what are we trying to do? We are trying to understand the coefficient of x raised to n in this series, right, and well, the coefficient of x raised to n in this series is the same as coefficient of x raised to n minus k in this part, right. This is what we saw. So, if we understand this series, we will understand this series, right. So, that is what we were trying to do. So, we want to do this partial fraction decomposition, right. So, we wanted to find these numbers, that is where we had stopped, fine, right. So, we want to find these numbers, okay. What are you doing here? Okay. Okay, so how do we find AJ? Right. So, what we do is you multiply throughout by the denominator 1 minus jx, clear the denominator and substitute x is equal to 1 by j, everything else will vanish, only this term will survive, right. So, let us multiply by this, right. So, it is AJ plus let us say L not equals to j, right. So, we have this identity. Now, if you substitute x is equal to 1 by j, there is a, right. So, this and this cancels. If we substitute x is equal to 1 by j, all these terms will cancel out, right. Only this will survive and we will get that AJ is equal to whatever is this. Is this clear what we are doing? That is how we solve for these numbers, right. So, you clear the denominator for the number you are interested in and substitute something that will make everything else vanish except for that number, right. So, if you substitute So, what do we get here? So, all this disappears, this is 0, we get that Aj is what? So, it is here, right, 1 minus k times k by j, 1 minus k minus 1 by j, all the way up till 1 minus 1 by j. So, this will be 1 minus, so the term corresponding to j is missing, and then we continue with j minus 1 by j all the way up till, right. So, how can we simplify this? Right. So, let us clear the j up here. So, how many terms are there? K minus 1, right, k minus 1. So, j raised to k minus 1, j minus k, j minus k minus 1, j minus j plus 1. And what is this? So, we want to write it in terms of some factorial, right. Let us flip these signs so that we have k minus j, k minus 1 minus j. Let us flip these signs. So, we will add same number of signs. Okay, that is why please be alert, this is post lunch, okay, and this is a bit not very nice. Okay. So, what is this? Something I do not know what it is turning out to be. Oh, something nice is not happening. Yeah, let us stop here, right. So, this is 1, right. So, we should stop here. This is 1, j minus j plus 1 is minus 1. So, that is 1, and then it starts again from, so this is j minus j plus 1. So, maybe we should not pull out all the negations. See, this is going down from k minus j all the way up till 1, and then it picks up again 1 to j minus 1, right. So, we should only pull out the first k minus j here, I think, and this is j factorial, j minus 1 factorial, and this is k minus j factorial. Is this correct? Does this look correct? Yeah. Right. So, it goes all the way up till here, this is 1. So, this is roughly, this is k minus j factorial, then this picks up again 1 to j minus 1. So, that is j minus 1 factorial, and we have just flipped these many signs. Okay. So, now we have some ugly expression for these numbers. Now, we have to go back. What are we interested in? We are interested in the coefficient of x raised to n minus k. So, x raised to n minus k in this, all of them, their sum is the Stirling number of second kind, right. So, I am not sure. So, the coefficient of x raised to n curly k is the coefficient of x raised to n minus k in this sum, right. So, what is the coefficient of x raised to n minus k in this series, right. What was the 1 upon 1 minus alpha x was coefficient of x raised to whatever was alpha raised to whatever, right. So, 1 upon 1 minus let us recall that. So, coefficient of x raised to L in 1 upon 1 minus alpha x is just alpha raised to L, right. So, we are interested in coefficient of x raised to n minus k in all of these. So, what we have is, by equating the coefficients, n curly k is the sum j from 0 to k a j, and so here the coefficient is j raised to n minus k. Okay. So, it is that is a, I am not sure how satisfied it is, but that is a formula for the number that we are looking for. Okay. So, if we substitute this here, we will get minus 1 k minus j raised to k minus 1 into j raised to n minus k is j raised to n minus 1 upon these factorials. Okay. So, if we multiply and divide by k factorial, then this is slightly more easier to remember. Okay, is it okay, so it is some kind of a weighted combination of binomial coefficients. Okay. So, here is a question, is it a formula for the number, the Stirling number of second kind? Is it a closed form expression? It is. We started from a recurrence, we have got our expression, right. Is it now, if somebody was to ask you, but hey, okay, this is fine, exact, but how large is this number? Can you give me any idea of how large is this number in terms of nk, right? Is it obvious how large is this number? How is it growing with k, with n? Then by that expression it is not satisfying. You can't get a feeling for that number by just looking at that expression. Okay. But still, having a formula, an exact formula is helpful, and the reason is, we were interested in not only this, we were interested in the other quantity, right. The total number of partitions of a set of size n, right. We were interested in the Bell number, which was all the partitions that you can have. Right. So, the total possible ways of partitioning n into non-empty sets. Right. Now, can we use that formula to find something about this number, get a closed form expression for this number, and then reverse engineer it to get a generating function and a recurrence for this number. Okay. So, one thing I will maybe not do it now is this formula has a very nice property. Okay, what is the property? We note that n curly k is 0 if k is more than n. Right? There is no way you can partition a set of size n into more than n parts. Right? So, this number is 0, by definition it is 0. Now, is that expression, that summation, is that 0? Is this 0 if k is greater than n? Right? It does not look like there is no relation between k, n and whatever is that. Okay, but surprising thing about this summation is that if k is more than n, then this vanishes. Okay, how do you see that? Okay, so the idea is the following. What is this? This is can you what is this number? Can anyone tell us what is this number?
1 minus x. Minus x the whole power k. Coefficient.
No, not coefficient. 1 minus x raised to whole k, but there is no x here. What is the x that sum of coefficients? That is right, but what is that sum? It is 0, x is equal to 1, right? This is what this is. If you forget about this, for instance, so this is this is 1 minus x raised to k, and you evaluate it at x is equal to 1, right? 1 minus x raised to k would have an x raised to j here, but if you evaluate this at x is equal to 1, you will get this number, right? That means this number is 0. Okay. Now, what will you do? Okay, now take 1 minus x raised to k, you differentiate it once. Sorry, what did we have here? J raised to what? N, right? J raised to n, right? So, let me say, let us take j, okay, and 1 minus x raised to k. Okay, how do I get j again? You take this, right? This is x raised to j here, differentiate it, right? This is equal to, right? This we all agree. Forget that 1 upon k factorial. This is true, right? That this polynomial is equal to this, right? Now, if you differentiate it once, what will happen? You will get j x raised to j minus 1. This will be k 1 minus x raised to k minus 1 up till some sign. Again substitute x is equal to 1, you will still get 0, right? This side is 0, so this sum is also 0. If you do this n times, what will you get? Some k minus n here, j raised to n, some x raised to j minus n, something like that, right? If k is more than n, substitute x equals to 1, this will still be 0. Okay. So, roughly that idea. So, what that means is, when we pull that thing here, we will write this k from 0 to n. So, let us substitute that formula. Whatever it is. Let me write this expression since it's the same thing. So, I drop this. So, this number is equal to this double summation, right. So, whenever you have a double summation, what do you want to do? You want to change the indices, right. So, that the same sum has two different ways of writing. You want to switch the indices and simplify the sum, right. But we want to use this observation that for k greater than n, this is 0, this is equal to 0. Okay. Right. So, how do we use that? So, this is saying okay, this is true, but if you let k go beyond n, this term will anyway vanish, right. That is what that observation is saying. You do not have to stop at n, you let it go beyond n, this will automatically vanish. So, that means you can drop both these quantities, maybe not this, you can drop this quantity, this sum, the limit of the first sum, right. And let us switch now. Okay, j is going to whatever, k is greater than equal to j, that is the only constraint, and the sum remains as it is. Okay. Now, nice thing is this part is independent of k, so you can pull it out of the second summation. Okay. Is this clear what we did here? I mean a slight maybe a trick of hand, but this the observation that if you have till n here, it does not matter, you can forget about n, take n k to infinity, the sum will anyway vanish. So, you can forget about this first upper bound. So, you can take the sum all the way to infinity, k only has to be greater than j. So, we do this, j is non-negative, k has to be greater than j, these two terms are the same. Okay. What is this sum? This is some nice series, if you have seen this, and so there are few series that we have to keep in mind. One is the geometric series, we are all familiar with. This is the exponential series, right. So, what is this? This is k greater, so k is greater than equal to j, so we can just write L greater than equal to 0 minus 1 raised to L factorial, right. So, this is, what is this number? E to power? No, it is a number, right, there is no n here now, it is just 1 over e. 1 by e, right. So, this is a constant and you have that. The nth Bell number is this sum. Okay. So, the nth Bell number is this infinite sum. Okay. So, we have a formula for the nth Bell number. Is it satisfactory? Well, maybe not, right. If you want to compute the nth Bell number, you can't use this summation. At least you will have to do some kind of approximation to this infinite sum and say that when that approximation is below half, you have your number, something like that. Okay. And it may not be a nice idea because this may not be converging very fast. So, even though you have this expression, you do not have a nice way to compute the number itself. But nevertheless, at least we have some formula for this. So, now we are going the other way around. So, what have we done? We started with this Stirling numbers, we had a recurrence, we got the generating function, from the generating function we got a formula for the Stirling number of second kind. From that formula, we have now obtained a formula for the nth Bell number. Okay. So, now what we want to do is, can we find a generating function for the nth Bell number? Can we find a recurrence for the nth Bell number? If you have a recurrence, you can compute faster. Okay. So, that was the inverting the equation, right. So, recurrences give us generating functions can give us recurrences. Okay. So, what generating function shall we, let us say b of x we define for the nth, for the sequence of Bell numbers. Okay, and if we substitute this formula, we will get so this is I mean the generating function that we have seen for the, right. If we follow our pattern that the generating function for this sequence is of this form, then we will get this thing. What does this look like? Well, you can again swap the order, and what is this sum? This is the geometric series, right. So, this is okay. So, it looks like, okay, this is what we end up with. It is an infinite sum of these fractions. Okay. So, from at this stage we are stuck with this, we have nowhere further to go. Okay. But if you look at this number really, especially this denominator part j factorial and so on, you know, this number, the way it looks like is, it looks more closer to the exponential series than to the geometric function, geometric series, right. So, there is no hard and fast rule on what clothesline you choose, that is a choice that you have. You can choose this as your generating function. This is called, what we will see now is the ordinary generating function, because this is the ordinary power series. But who stops you from taking the exponential generating function? Okay. So, that choice is with you. What kind of closed line you tie on the sequence on. This sequence is given to you, the closed line is your choice. Okay. And in this case, it is more natural to work with, this is called the exponential generating function. So, if you do that, well, let us see where we do that. So, how do we simplify this now? Right, again let us switch the order, j comes outside, n goes inside. Right, what is this series? Okay, so what do we have to remember? E to power x is x raised to n by n factorial, right. E to power x is the generating function, the ordinary generating function for the sequence 1 upon n factorial. That is another way to look at it, right. E to power x is the ordinary generating function for the sequence 1 upon n factorial. Right. So, what is this? This e to power jx, right? Let us write e to power x is to j. What is this? E to power exactly, yeah, it's e to power x minus y. Okay. So, whatever this Bell number, whatever this number is, it has a very nice, a very small, easily memorized exponential generating function. Okay. That's a pretty large number. If you start to think of it, it's like the coefficient of this doubly exponential series. So, now that we have such a nice formula for the generating function, the exponential generating function for our sequence, well, can we get a recurrence from this? Okay, so you will not perhaps remember this thing, but you can always remember this thing, and from this you can derive that. So, we have that b of x is e to power x minus 1. Okay. And so, this is what we have derived, that the exponential generating function for this series is, this sequence is this function. Okay. So, what do we do? Since there is a double exponential, let us get it down. So, take the log of this. The log of this sequence is just e raised to x minus 1. Okay. See, this is the kind of manipulation that we can't do with the sequence, right? If you are given just a sequence, you can't take, what does it mean to take the log of the sequence? Doesn't mean anything, right? But you can take the log of the function. Okay. Not only the log of the function, if you differentiate this, what will we get? So, what is the derivative of log of f of x? F dash by f, right? The logarithmic derivative, the derivative of log of x or ln of f is right. So, what do we get here? So, we get the derivative of this upon this. So, let us multiply this. The derivative of this is what? E to power x right. So, let me write e to power x is summation of j equal to 0. Let us write it as k okay. So, the derivative of this function is the product of these two functions, right. Now, let us take if we want b, let us say bn here. So, what is the coefficient of x raised to n here in the derivative? The coefficient of x raised to n in this derivative. So, if you pull in the derivative, this will be n x raised to n minus 1 upon n minus 1 factorial. right. So, this is saying this sum is equal to that. So, coefficient of x raised to n is bn plus 1. So, if you compare the coefficient of x raised to n on both sides, we will get bn plus 1 on the left. What is it on the right? It is the product of these two, x raised to k, x raised to j, k plus j should be equal to n, right. So, what is the coefficient of x? How will you get the coefficient of x raised to n here? It will be x raised to k here, x raised to j there, such that k plus j is n. Yeah. So, it is a summation of upon so bk. Do you understand this? Right, the coefficient of x raised to n in this product is, right, all such terms, sum of all these things, right. K plus j should be equal to n. I am just k and n minus k. That is what we have done. Sorry, it is not bn plus 1, it is bn plus 1 upon n factorial. Right. So, bn plus 1 upon n factorial is this. So, if you move this to the right side, you have a nice recurrence for the Bell numbers. And what is this saying? The n plus 1th Bell number is, it is not just the sum of all of them, it is this weighted sum with the binomial coefficients. Okay. Right, and this is much more amenable to computation. The earlier thing where we had that infinite sum, Bn is some j raised to n upon j factorial. Right, this, I mean, you can compute, it's some approximations you have to do and so on, but this is nice. This is a recurrence. You can write a nice recursive algorithm, maybe dynamic programming or something to code this up. Is it clear? Any questions? So, what did we do? We started with recurrence for the Stirling numbers. We got a formula for the Stirling numbers using the generating function for the Stirling numbers. Then we derived a formula for the Bell numbers, then a generating function for the Bell numbers, and then a recurrence for the Bell numbers. Okay. So, from all the best. That is what you may not intuitively think of this formula. It is not easy to come up with such a formula. That is where it's now this is science. You can just do this as an algorithm. To directly come up with this formula, you have to have, I can't imagine, but maybe somebody can. You need a very combinatorial argument. Right? How do you prove identities? Right? Somebody can ask you to prove this. Hey, prove this identity that n plus 1 Bell number is the sum, weighted sum of all the previous n Bell numbers. Right? Either you will give a combinatorial proof, right? You will say this is counting something, and if you do it in some different imaginative creative way, you can count it the same thing in this way. Right? That is a combinatorial proof. You set up two sets, right, or one set, and you count it in two different ways. It's the same thing, right? This is saying forget about all that combinatorial way. Just how do you prove an identity? You prove that the two generating functions are the same. Okay. So, for example, you should try to prove the following identities. So, try it both ways. It is a good learning experience. So, if you take the sum of the first n Bell numbers, sorry, Fibonacci numbers, you get the n plus roughly the n plus 2th Fibonacci number. Okay. So, you can prove it inductively, naturally you will try that, but if combinatorially it is very hard, you have to come up with something that counts the Fibonacci numbers. But what if you were to try to prove it using generating functions, right? What is the generating function of for the left side? What is the generating function for the right side? If the two functions are the same, the identity holds. Okay. Choose. This you can try combinatorially also. Right, that this binomial identity holds, and this maybe you have seen. Okay. So, these you can try to prove combinatorially. You set up, well, this is counting something and you show that this is also counting the same thing, this is counting something, this is a different way to count the same thing. That is called a combinatorial proof of the identity, right. The other is, do not think of this as numbers, think of this as part of a sequence, do the generating function, compute the generating function on the left, you choose n, m, whichever one you want, n, m, you know, and prove that the generating functions for the two sequences are the same. Right. This side generating function is the same as this side generating function. In fact, in some software systems you can check these identities, and there is an algorithm which does exactly that. It is called the Zeilberger-Wilf algorithm. So, Doron Zeilberger and Herb Wilf, we have seen his. So, he is another big guy. For example, he really hates proving combinatorial identities. He is a very eccentric person. You will see a lot of his papers are with someone named Eckhard. So, a lot of his papers have a joint author. There is some the author name is Eckhard, and that is the name of his computer. Okay. So, his papers are joint work with his computer, because for him that is an assistant who helps him do his proofs. Okay. So, if you give him such an identity, he will not prove it in this combinatorial way, he will just give it, he will use his algorithm and just say this is the identity, use this generating function idea, prove the identity. Okay. So, they have an algorithm which does exactly that. Okay. So, you can try to do the same. So, what ideas will such an algorithm need? You know, how will somebody prove such identities? If you were to design the algorithm, you need some basic notions. Right. So, what is the algorithm going to do? It is going to manipulate these generating functions, right. That is the idea. It is going to manipulate them, differentiate them, multiply them, and say, well, there are these sequence of operations that you can do which are well defined, and you get these generating functions, and these two are equal. If they are equal, their coefficients are the same. Okay. So, the formal background for all this is the theory of formal power series. we'll start with formal power series. Okay. So what is that? So if you have some sequence, you associate with it. What we have been doing so far, the formal power series is just this sum, right? Okay. So why the emphasis is on this word formal. Okay. So when we think of power series, we have, who was this? We always worry about convergence and so on. We have to, oh, what is the radius of convergence of the power series and so on, right? So we are thinking of it as a function that we are going to evaluate on a certain region of maybe the real axis or the complex plane or something, right? So power series, always we worry about notions of convergence. Formal power series says forget about all that analysis part. It has a role, not now, but it has a role. But we will only manipulate them as algebraic objects. Okay. So where is this field that they are, or this algebraic set where they are sitting in, right? So it's so if you have two such series, you can clearly add and subtract them, right? Right? They have two series, formal power series, their sum and differences is well defined, right? Right? The formal power series for the sum is the sum of the formal power series, right? Formal power series of the sum is the sum of the formal power series. Formal power series of the difference is the difference of the formal power series, right? Okay. So if your coefficients are coming from some ring R, so what is a ring in algebra? Not the Lord of the Rings ring, right? Any set which is closed under addition, subtraction and multiplication, which has additive identity and multiplicative identity, and all these operations behave what you expect them to. They distribute, they are associative, they are commutative, whatever, right? So we will work with commutative rings. So we have all the nice things. So if you want, just think of integers, right? For most of our cases, all these numbers are coming from integers. They are integers, or maybe the worst case, you can go to rationals, right? So what are we saying? If you take two such formal power series, their sum is a formal power series. You take two such formal power series and you can multiply them also. Sorry. Right, you can multiply the formal power series, and the coefficient that you get, Cn, is the convolution. This is called the convolution of the coefficients of these two power series, right? So Aj's are going like that, Bn's are going like that, right? This thing is called a convolution. It's a natural way that will define product. So you can add and subtract, you can multiply, and you still remain within your, it's denoted like this. Okay. So this is called the ring of formal power series. This is the notation. So if you have only one bracket, it's the set of all polynomials, right. If you put two brackets, it is a set of all formal power series. Right. So, what does it mean? The elements of the set you can add, subtract, multiply, you remain within the set. Is this fine? Okay. So, this is now if you are going to design a data structure for your algorithm, what will you do? You will have a data class or whatever, some class, something which will be the coefficients are coming from a ring structure. So, your whatever they are integers or floats or something that has a ring structure to it. On that you will define this class of rings. The nth coefficient you can write it as this in this form. And you are defining manipulation of these structures, right. To add the coefficients, to multiply it in this way, convolution. Do we understand these operations? Right. Three operations, right. So, they are closed under these addition, subtraction and multiplication. Okay. So, when can we say that formal power series has a reciprocal? Right. So, you have f, which is this summation. When does there exist another series G such that f times G is the number one, the one in your ring, coefficient ring, right. So, when is there a reciprocal? For example, we have seen that what is the reciprocal of summation of x raised to n? Huh? No. What series do you multiply with this to get 1? Huh? 1, no. So, what series will I multiply with this to get 1? X just disappears. Right. What is this series? 1 by 1 minus x. What does that mean? That is what we said, right? 1 minus x is the inverse of this. That is what it means to say that this is 1 by 1 minus x. That this series 1 minus x, it is only two coefficients, 1 and minus 1. When this multiplied by this, you will get 1, right. Now, the question is, if you have an arbitrary series like this, when can you find a G such that x completely cancels out? No, now there is a n, right, there these coefficients are here. Now, there is only one here. Right. So, it is a system of equations, right. So, what do you want? Only the constant coefficient is 1 and all the other coefficients, all those things vanish, right. So, f times g is that. So, constant coefficient is 1 means let us say g was bn x raised to n. So, this says a0 b0 is 1 and all those other a1 b0 plus a0 b1 is 0, all the other terms vanish. Okay, that is true. So, the reciprocal exists if and only if this infinite system of constraints hold true. So, do we really need all of this? So, what if A naught was 0? Can this ever have a solution? No, right. So, A naught better be non-zero quantity, right. Okay, let us say A naught, since A naught B naught is 1 and we are in a ring, A naught is actually should be 1, right. If A naught is 1, B naught is also 1. Now you know A naught is 1, B naught is 1, you know what A1 is, you can solve for B1, right. Right, B1 is whatever minus A1 B naught by A naught, right. So, you can solve for B1. In the next one you know B naught B1, you can solve for B2, you know A naught A1 A2. So, you can, there is a unique solution, right. So, if A naught is 1, there is a unique series of this form which will satisfy this constraint, and this is if and only if, right. And in our case, in fact, the constant coefficient was 1, that is why we have a solution. Okay. So, reciprocal exists if and only if the constant coefficient in your sequence is 1. And that is what, so when we are saying, you know, when we are writing this, so for the Fibonacci sequence we wrote that the generating function was f of x was x upon 1 minus x. What do we mean by 1 upon 1 minus x square? It is exactly the reciprocal of 1 minus x square, right, because the constant coefficient is 1, there is a reciprocal. So, this is what we are saying here is this is x times reciprocal of this. And which is a unique series which exists because the constant coefficient is 1. So, that is what we are saying here. Okay. So, even though it looks like we are working with, you know, ratios of polynomials or something, actually we are still in that ring because the inverse is reciprocal is well defined if you have a constant coefficient. Okay. So, let us maybe do a little bit of, I need one more thing. So, we will also define the derivative of a power series, formal power series f. So, that will be denoted by f prime, which is the series whose coefficients are this n times a. Okay. So, you can ask now, okay, which power series has the property that it is its own derivative? Yeah, but in this form, you are right. So, if f is equal to f prime, then there is a constraint here, right. So, that we have to show that only e power x or a multiple of e power x is the only solution. Okay, let us now do. So, what we will do now is we will set up a dictionary. If you want, you have ordinary generating function or a formal power series f. I will write it like this for the sequence a n, right. What does this mean is f of x is a n x is right, this formal power series. So, F is the formal power series associated with this sequence, right. Now, what we want to do is, okay, is there a way to manipulate the formal power series so that we get the formal power we get for some sequence that we are interested in, which depends upon the right side. Okay. For example, if what is the formal power series if you shift one index for a n plus 1? Right. Given that f is the formal power series for a n, what is the formal power series for a n plus 1? This sequence. So, let us do this. We did this for the Fibonacci numbers, right. So, what is this? F is a naught plus a1 x plus blah 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 a2 x square, and the series we are interested in starts with, what is this? This is a1 x, this is sorry a1 plus a2 x plus, this is the series with, yeah, right. So, this is the series that we are interested in, this is the series we have in hand. So, what is this equal to? What we did, f minus a naught divided by x, that is the series corresponding to this, right. And that is what we did for the Fibonacci numbers, exactly, right. So, we had that f n plus 1 is equal to f n plus f n minus 1, right. What was the series for f n plus 1? F minus a naught by x. So, you can do the same. What is the series for a n plus 2? Right now, this is a2 plus a3x plus a4x square and so on. Right, same idea, move everything what is here to the left, divide by that appropriate power of x, right. Right. So, how if you can use this, if you instead I had started like this, right, if I write it this way, the Fibonacci recurrence, then now I do not have to multiply by x raised to n, do all that. We can directly use this relation to say that the left hand side will give me what is f naught f minus x square f by x plus f. Directly from this we can write that, right. And the sequence for this is the sum of these two sequences. What is the sequence for this? Is of this form. Sequence for this is this form, and f n is f. Okay. So, this is what we had done, I mean earlier explicitly. Now, you can make it as part of automated part, that if you are interested in a sequence a n plus k for some fixed k, you just have to drop the first k coefficients here on the numerator, divide by x raised to k. Okay. What is the sequence for n times a n? You understand the question? So, now we know the sequence for a n is f. So, what if you multiply by n, the nth coefficient by n? Huh? We almost have it, right, except we are missing an x here, it's off by 1. So, we just have to multiply it by, right. So, the sequence for n times n is x times the derivative of f. Let me write it like this. So, treat derivative as an operator. So, x d times f. What about n square n? Right. So, x d gave us 1 n. Huh?
X square double derivative.
Yeah. So, no, not double derivative, but one derivative we have to multiply by x to shift it back, right. You take the derivative, you have fallen down by 1, you hit by x to get it back above. You take the derivative, it is almost there, you have to shift it again by x. So, it is x d 2 times, or what we will write is x d square. Okay. So, it is an operator, but we are writing it as multiplication, right. So, now what you can say is, okay, what if there is some polynomial in n? Right, let us say there is some polynomial of n, g is some fixed polynomial, we are evaluating it at n and multiply it with the nth term. What is the corresponding series for that? Huh? Yeah, intuitively it looks like. What will you do? So, if you have n square, you are doing x t. If you have n, you are doing x. So, right. So, if you add them up along with the coefficients of g, you will get right. Just substitute this operator in place of x. Do that operation. It is not that you do not have to do. So, you have to differentiate f appropriate number of times and so on. Okay. So, how do we use this? So, what is the generating function for this sequence? Okay, so, the nth term is n square plus 1 upon n factorial. Right. So, there is g of n is n square plus 1, a n is 1 upon n factorial. Oh, what is the sequence whose coefficients are 1 upon n factorial? What is the ordinary generating function for the sequence whose nth coefficient is 1 upon n factorial? E power x, right? That is what we had seen, right. So, 1 upon n factorial, what is the generating function for this? What is the sequence corresponding to this? Summation x raised to n by n factorial, which is the exponential series, right. So, this is, so what is this saying now? If you want, the series for 1 upon n factorial, what is the series for this? Is x d square plus 1 applied to e raised to x. Okay. It is just manipulation now, you do not have to do all that calculation, you just have to do, okay, take this polynomial, apply it to this series, right. So, this is e raised to x and you have to do this x d e raised to x. X d x derivative of this is again this, so this plus, right. So, x of e raised to x plus. So, that is the series. Okay, so, x e raised to x plus x square e raised to x plus 1. So, this is the generating function for this series. Okay, so one last thing. Right, so this is continuing that. So f is the series for an, g is the series for bn, then f times g is the series for, no, product is the series for the term whose coefficients are the convolution. Right? This is just what we had seen by definition of multiplication of two series. The multiplication corresponds to the series whose coefficients are of this form. Right? How do we use this thing now? So, can we use this to so what is the series found by the sum of all the terms up till the nth term? So, f is the series corresponding to an. Now, we want to find the series whose nth term is the sum of all the previous terms, right. So, what is the b's here? What are the b's if you look at it? B's are all 1, right. And so, what are we saying? Multiply it with a series whose coefficients are all 1. Which series has all coefficients 1? Geometric series, right. So, what is this? This is f upon 1 minus x, right, the reciprocal of the geometric series, right. So, f divided by 1 minus x, the coefficients of that series is the sum of everything, all the previous n coefficients. Now, you can use this to take sums of anything, right. You want you can do it that way or this way, either way is okay, right. What is the series whose nth coefficient is the number n? So, what is this saying? Take a series which has entries 1, all the coefficients are 1. If you hit that series which is 1 upon 1 minus x, it is the sum of everything before, right. So, this is what, right. If you multiply x raised to n with itself, right, what will it say? It will say add up all the coefficients up till n. Okay, now we want the sum of the first n numbers. What do? Multiply it again with itself, right. So, right. So, the convolution with itself is right. This was coefficient was n. If you multiply it again with 1 upon 1 minus x, it will start summing up the n's, right. So, all the coefficient numbers from 1 to n, it will sum up. So, this series, the series corresponding to this sequence is this. Okay, we can do it that way also, derivative, right. You can check the series which has n only will be an is 1, x times d times f is 1 upon 1 minus x. So, x upon 1 minus x whole square. So, I may be missing some x here. Okay, so what is the point of all these? These are rules now, right? What is this saying? You are interested in, you know this relation, from this relation you can derive all these relations, right? So now if you remember the identities that are given you in the starting, right? There was sums there, the last one had a sum, even the Fibonacci one had a sum, right? What is the sum of the first n Fibonacci numbers, right? Take the convolution of the Fibonacci series with 1 upon 1 minus x, right, and find that coefficient. Okay. So this that is the power of algebra. All those complicated summations, manipulations that we are doing are now simplified into these rules. You just have to apply these rules in your algorithm, encode these rules in your algorithm. Okay. And then your algorithm can automatically do the identity testing. So try to do that, those three problems using these rules if you can. Yeah. So one was to do it the way we started with, okay, try to figure out what is the genetic function for this and that, for the way we did for Fibonacci numbers. The other is to cleverly use these rules. Now we have figured this general principles, so use those to solve your, find the genetic functions. Yeah. So next what we will see is the same rules or similar rules are there are corresponding rules when we do not have, this is the ordinary power series, but when we will tomorrow do the exponential power series. So the Bell numbers, the series for the Bell numbers.